Okay, let's get started. Hi everyone, welcome to lecture 20. So last time we constructed interactive oracle proofs for machine computations, achieving simultaneously a linear size proof length and also a polylogarithmic, in fact, logarithmic query complexity. That concluded a unit of, I think, 5 lectures on constructions of interactive oracle proofs. And now we're kind of taking a step back and we're going to discuss a technique known as proof composition, which can be used both for PCPs and interactive oracle proofs for reducing query complexity. In particular, it is a technique that is used for proving the PCP theorem, which we haven't proved yet. So that's the goal for today, to talk about proof composition, and then this will kind of motivate other questions we'll have to deal with in the next couple of lectures. Okay. So we have seen techniques to achieve either a polynomial proof length and polylogarithmic query complexity, or exponential proof length and constant query complexity. Okay, so the first one was the construction based on multivariate logistic extensions, and the second construction, which in fact we saw earlier, was the construction based on linear PCPs and linear extensions. Okay, and you should ask, how do we achieve the best of both? Both polynomial proof length and constant query complexity. So today we'll learn about proof composition. Okay, it's a technique for combining two PCPs so that the composed PCP inherits the proof length of one and the query complexity of the other. Okay, and because in this case, at a very high level, we had good proof length in one PCP, but maybe good, but maybe not optimal query complexity. And for the other one, we had very large proof length, but optimal query complexity. We want to construct a PCP that has both. And intuitively, if we're going to apply this one to both, we're going to get, as I said, the best of both. And this technique of proof composition is precisely what is used to apply to constructions related to these to derive the PCP theorem, right? So we have essentially already proved this result, but for this achieving simultaneously polynomial proof length and constant query complexity. So in the next, today, in the next 2 lectures, we'll be able to prove the PCP theorem. Still requires a little bit of work. Today we will also learn about interactive proof composition, which is the analog of proof composition just for interactive oracle proofs. Okay, and just like you can use proof composition to improve query complexity of PCPs, you can use interactive proof composition to improve the query complexity of linear size IOPs. So for example, interactive proof composition leads to an optimal trade-off between proof length and query complexity, where it is known through this technique to achieve an IOP for a Boolean circuit satisfiability, where you have both linear proof length as bits, okay, and constant query complexity in a small number of rounds, in fact 3. So this is a powerful and general paradigm, and so that is what we want to talk about today. Are there any questions about the motivation? So today we just want to basically talk about the proof technique, and we'll see how to apply it later on. Okay, so if there are no questions, then let's jump right into it. So the high-level plan is that we'll have 2 ingredients, the 2 PCPs we start from, and one of them will be designated as the outer PCP, okay, and it will be for the target language that we care about. And the second PCP will be designated as an inner PCP. It will not be about the language we care about, it will be about some relation that has to do with the verifier of the outer PCP. Okay, we'll talk about this in detail. Roughly speaking, the outer PCP is the one that will have the good proof length, and the inner PCP will be the one that has the good query complexity, okay, at high level. We wish to construct a new PCP, the kind of composed PCP. This should say for the language, not relation. For language L, that has the best of both, okay? Now, the idea is going to, roughly speaking, to be to use the inner PCP to check the computation of the outer PCP's verifier. This sounds almost like a forced move, right? If we have an outer PCP that has good proof length but okay query complexity, we can either throw it in the trash, but that doesn't sound very wise, or we can try to like not run the verifier and then sort of run a PCP about its verifier. Like that's roughly the idea. And the way we're going to be doing it is somewhat reminiscent of the way that code concatenation works in coding theory for reducing alphabet size. Okay, so the designation of outer and inner is like reminiscent of that, if you're familiar with code concatenation. Okay, so we have this outer PCP, and we could be running. Oopsie. We could be running this outer PCP, but there's many queries that we don't feel like doing it. So the high-level plan would be to say, okay, look, why don't we just consider some augmented PCP that includes a bunch of kind of sub-PCPs, one for each choice of the outer PCP's randomness, and we're just going to run the inner verifier to check the statement on input X and randomness, in this case randomness row 2, the verifier would have accepted this thing, okay? Now, syntactically, some things are not making sense yet. We'll discuss in a moment in what precise way. For example, how can this guy reason about that guy if it's not even making queries to it? Well, it will have to, but right now we're just at high level thinking of the plan. So at a very high level, we're going to construct a new PCP where the prover will compute the outer PCP, one of it. It's fine, it has good proof length, so we can afford it. And then for each choice of randomness for the outer PCP, it's going to say, okay, I'm going to compute an inner PCP to try to convince the verifier that the outer verifier would have accepted had you run it on that randomness. Okay? And so this gives rise to a bunch of inner PCPs. And then it outputs the outer PCP and the inner PCPs specialized to each choice of randomness for the outer PCP. The way the verifier is at high level is going to operate, it's going to choose one of these randomnesses that it will, means that it will ignore most of the other ones, right? But it will be interested in a particular one. And it will run the inner PCP on the statement on some kind of inner instance, okay? That is the outer instance for the language and the choice of randomness, and it's going to be interested in the statement, is the outer verifier accepting on that randomness? And of course, this inner verifier has its own randomness row in. At high level, this is the plan, but there are some problems with this plan, okay? And we're about to kind of discuss these problems. In particular, there are some things that should kind of confuse you here. That said, other questions about this slide? Like, is it clear at high level, like what the plan is? We have an outer PCP. We are okay with the proof length. So here it is, we write it down. We're not okay with its query complexity. So we're not going to run the outer verifier. And instead, we're going to get some inner PCP whose query complexity we're fine with, but maybe the proof length not so much. But it's okay, right? Because the computation of the inner verifier shouldn't be the big computation we started from. So kind of the worst proof length applied to merely the computation of the outer verifier should be something that we can afford, okay? So they're making up for each other's weaknesses, and we want to try to inherit the good things from both, okay? At high level. Questions? This is the plan. Yeah.
Quick question. You mentioned when you were looking over the diagram that there would be at some point queries from the outer to the inner, and you had mentioned then that just wasn't represented yet because we're looking at it from a high level. That's also not noted. I'm just checking to confirm that I'm not missing it in the actual definition of P of X.
Oh, this is it's not here because these are also just I'm just writing pseudocode for this high-level diagram. Why? Because later I will be writing again pseudocode for what we actually do, and I will highlight the differences from this pseudocode, okay? But yeah, intuitively, you're gonna want somehow this guy to also say something about that one, okay? But, okay, we're gonna talk about this in the next slide, okay? All right, good question. More questions about this slide?
So I thought that pi n was prohibitively long, or it's the longer proof?
Yeah, so again, good question. So pi in has not very good proof length, so we cannot afford it to just run it on L, or at least the computation associated to deciding membership in L. But maybe if this outer verifier is simpler than that computation, we can afford running it about the computation of the outer verifier. Because remember, we are invoking the inner PCP not to check a computation about L, rather to check a computation about the outer verifier, okay? Which should be simpler than the computation about L.
I see, okay.
Okay. And again, so if you're familiar with code concatenation, this is something that may be familiar. The way you construct a good code via code concatenation is that you first construct a code with a constant rate and constant relative distance, but over a large alphabet, okay, for example, the Reed-Solomon code, and then you concatenate it with a code that is over a small alphabet, but maybe has like very bad rate. And rate is kind of the analog of proof length in our case, and the alphabet, at least in that setting, is kind of the analog of query complexity, okay? All right. So, yeah.
Could you repeat once why the inner PCP having proof length long doesn't matter here?
Well, it's not that it doesn't matter. It is being mitigated by the fact that, or at least the intention is that it will be mitigated by the fact that we are not invoking the inner PCP to solve the original hard problem about L. We are invoking it merely to help us check the computation of the outer verifier. But because this is a probabilistic proof about L, we expect this verifier to be simpler than the original computation, okay? So kind of, this is already like a simpler language to solve, okay? And because it's a simpler language, we can afford a bigger blow up, okay, in proof length relative to a smaller problem, because we kind of first take the original problem, kind of compress it, and then blow it up again, right? I hope that addresses the question at high level.
Yes.
Okay. Great. Okay, but so this is just a high-level plan, and there are some technicalities that will, in fact, bring to the surface issues that mean that basically this plan just doesn't work, and we're going to need to use specialized types of PCPs, and that there is a subject to introduce these types of specialized PCPs in this lecture, so that then we'll go back and construct them in the next couple of lectures. So what are the problems with the plan? Okay, so here's the picture from the prior slide. I'm just copied it here. So one problem is that it could be that every choice of randomness for the outer verifier, there is some PCP, depending on the choice of randomness, that makes the outer verifier accept, even when the instance is not in the language, right? Because soundness of the PCP says you fix the PCP, then you sample the randomness, and you have like some small probability of accepting. But if you first fix the randomness and you ask about the PCP, there's always one. Maybe they're inconsistent, and usually they're going to be inconsistent with one another. But what does this mean? It means that we need to be careful about what the inner PCP is proving. Okay, if the inner PCP is asked to prove to me the statement, does there exist pi out such that the out, given pi out, would have accepted specifically on this randomness, well, this statement could just be a tautology. It could be always true, no matter the choice of row out, okay? So somehow the inner PCP should not be reasoning about satisfiability, but about some other type of problem. And an approach that we're going to use to kind of address this is that the inner PCP should in fact be a proof of proximity. Okay, so we've come across proofs of proximity before, most notably when we talked about the IOP of proximity for the Reed-Solomon code. But here we'll kind of come across them sort of in their full generality about sort of general languages. Okay, so what we want is the inner PCP to say that a specific local window, local view of the outer proof that was fixed before the randomness was sampled, that window is, either accepting or rejecting, right? So compare the question: is there a satisfying local view for this kind of input to the outer verifier, or is this local view derived from the given pi out satisfying for this choice of instance and randomness, right? So somehow we have to be able to say, inner PCP, please check something specific about this restriction of the outer proof. Okay, that's going to be our approach. So intuitively, kind of syntactically, we're going to want to run the inner PCP on a particular witness, okay, and the witness will be selected to be the window or the local view of the outer proof that is relevant for this execution of the outer verifier, okay? And we want to ask this proof of proximity to be specific about this one, not about some local view, about that local view, okay? Now we'll define proofs of proximity in detail in the next slide, but this is a problem. I mean, this at high level, we want to talk about a particular witness, not just some witness, about a particular local view, not just some local view, okay? The local view that we derive from the full outer proof, okay? So that's the approach we're going to be using proofs of proximity for the outer PCP. Again, all of this will become formal very soon. I'm just kind of raising the things. In particular, when I have this V in taking that one, it means that, it will reason about, some particular set of locations that we don't have the query budget to touch ourselves, but we can consider them like a large witness about which we do a proof of proximity. A second problem is that we actually cannot hope to detect whether, with a small number of queries, whether a particular local view is accepting or rejecting. Because look, this local view consisted of some number of queries, some number of locations that we specifically did not want to read directly because there were too many queries for the outer PCP, okay? And the size of this local view is smaller than the original. It is a sample, a local view from the outer proof, but we don't have the query complexity budget to query all of them. That's why we're doing proof composition, right? Okay, but if we cannot see the local view in full, we cannot expect to detect in a small number of queries whether it is accepting or rejecting, okay? So somehow the outer PCP should help the inner PCP creating some gap, okay? And so the way we're going to kind of say this is that the outer PCP should be robust. Namely, when X is not an L, it's not that with high probability a local view is not accepting. It is far from accepting, okay? This is a so-called robust soundness property, okay? So the outer PCP, in the no case, in the soundness case, when X is not in L, most local views are in fact far from accepting, so that we are simplifying the task of the inner proof system. It merely has to distinguish an accepting view from one that is far from accepting, okay? As opposed to, is it one symbol away that we cannot hope to do with a small number of queries, okay? So in sum, we're going to need some kind of a collaboration between an outer PCP that is robust and the inner PCP that is a proof of proximity, okay? And this is just intuition, and the next two slides I have to define each of these notions formally, so that then we can go back and prove proof composition using these notions. But again, at an intuitive level, is it clear why we need both robustness and proximity? Robustness creates a gap between accepting and rejecting views, and proximity tries to distinguish between accepting and rejecting specific views that are given to you as witnesses using a small number of queries, much smaller than the size of the local view. Just pause for a moment because it's important to understand this. Okay, remember that we have like kind of two levels. One is the original problem. Then kind of we apply the outer PCP. We kind of reduce the number of queries from trivial to something, but that something we're not happy with. This something is the size of local view, and then we're going to invoke yet another inner proof system to reduce the query complexity even further, okay? So that in the end, we are actually not querying an entire local view. Okay, that's where our query savings are going to come from. Okay, so this is just to motivate the notion of robustness and proximity. Now we need to define it. Okay, so I want to define is a robust PCP and then a PCP proximity. Okay, so robust PCPs. So remember that soundness in the PCP states that the probability that the local view is accepting is small. Robust soundness strengthens this to require that the probability that the local view is close to accepting is small. In other words, with high probability, a local view is far from accepting. To say this formally, we're going to have to restrict our attention specifically to non-adapting verifiers, namely the ones that just ask all their queries at once without waiting for the answers of prior queries. And we're going to view non-adaptive verifiers as made up of two algorithms. A query algorithm that, given the instance and the choice of randomness, determines which indices of the proof it's going to inspect. And then a decision algorithm that, given the instance, the answers, and the randomness, it decides whether to accept or not. Okay, and that is, the way you can decompose a non-adaptive verifier. Okay. Once you have this decomposition, you can define the relation of accepting local views. Okay, so remember, relation is a set of pairs where you have the instance and the witness. Okay, the instances are going to be instances for the original language L, okay, and choices of randomness for the PCP verifier. And a witness is a choice of answers indexed, by the indices. Sigma is the alphabet here, and when I say to the power Q, remember here is the indices that we're inspecting on this instance and on this randomness. And we're considering all instance witness pairs that make the decision algorithm say, yes, I accept. Okay, so these are all the accepting local views for the verifier. Okay, and notice that maybe I should be more precise here. Verifier, about the language L, right? So that's where X comes from. We don't need to say the verifier knows what is L, right? So that's why it's not explicit in the definition, but there's some implicit L underneath. With this set, we can define a robust PCP. So we're going to say that a pair PV is a PCP system for a language L with so-called robustness parameter sigma if two things hold. First, completeness is as always. We just ask that when X is in L, the honest prover makes the verifier accept with probability that is above, this should be above 1 minus the completeness error, which is usually 1, okay? So this is as always. The robust soundness condition is as follows. Let's parse it. It says for every X not in L, for every PCP, let's look the probability that the local view is sigma close to some accepting view, right? So, and now what is this? What is this notation here? Oopsie, let me just. Here I'm saying take the relation of a local views and restrict it to all witnesses, all local views that are accepting specifically for the choice of X and rho. Okay? So these are all the local views that would make the decision algorithm accept when given the X and the rho that we're discussing here. X has been fixed outside the probability statement. Rho is part of the probability statement. So we're asking how close is this local view to being accepting? And we're going to say, well, we want the probability that it is too close to be small. Okay? And we can see that this is a strengthening because standard soundness is the above definition with sigma equals 0, right? Because typically we want to say the probability that you have literally an accepting view is small. Well, that is an accepting view is when this is the case, but it is exactly when your distance to some accepting view is 0. Okay? So a standard PCP is a robust PCP with robustness parameter equals 0. Okay? And in fact, actually, not just when the robustness parameter is 0, but anything between 0 and less than 1 over q, because the strings that we're comparing have q symbols. Okay, so the distance kind of is a step function that goes from 0 to 1 over q, 2 over q, 3 over q, up to 1. So like a fractional distance of anywhere between 0 and strictly less than 1 over q, that is also 0. Okay, just to kind of get calibrated. The point is that local view is not that large. Okay, so kind of this stepwise, the distance function behaves stepwise, where q is not that large. That is the definition of a robust PCP. Other questions about how we formalize this? Again, this infrastructure is to just be able to talk about local views so that once I have accepting local views, then I can compare the distances of what is the local view that I'm inspecting. Okay? So let me pause and see if there are questions. This is the one slide that we have about robust PCPs. Then I have one slide about PCPs of proximity, and then we're going to prove the composition theorem. Everybody comfortable with the notation? Okay. So now we're going to talk about PCP of proximity. So PCPs of proximity are abbreviated PCP usually, and a PCP is to prove for a given instance X and also it's given candidate witness W that W is close to a valid witness for X if one exists. Okay? In particular, PCP verifier is given oracle access to X and to oracle access to W. Okay, so it's given explicit input X and oracle access to W. Okay. Now, PCPs of proximity are not about languages, they're about relations, because you have to be able to talk about witnesses explicitly. So give me a relation, here it is, of instances and witnesses. Okay, so for example, you can think about circuits and satisfying assignments. Okay, we're going to define the language of R to be, you project on the first coordinate, and that is the language. So that's just the notation. We say L of R, you just project on the first coordinate. That's like, you kind of forget there are witnesses. And also, we're going to be using the notation kind of already used in a special case in the prior slide, R brackets X. These are all the valid witnesses for a particular instance. Okay, so if you have a certain instance in mind, you can ask, well, what are the witnesses for it? There's going to be a set for it. This set could be empty. Like if the instance is not in the language, then that just means that there are no valid witnesses and this set is empty. Okay? Now, we're going to say that PV is a PCP of proximity system for a relation R, not a language, a relation, with proximity parameter delta if, now, completeness is basically unchanged, but there is an important syntactic change from a PCP. Unlike a robust PCP, which is literally a PCP of proximity is a variation on a PCP. We'll see some other time that it implies it, but it's syntactically not a PCP. How it is not syntactically a PCP? Because the verifier specifically gets oracle access to the W that you want to talk about. Okay? In addition to whatever the honest prover says it wants to give to the verifier. That is the proof of proximity. Okay, that's kind of what the system decides to put there. But the witness comes from the relation. Okay, nobody gets to touch it, right? It's kind of like a trusted oracle for the verifier. And again, here I have the same typo as before. This should be at least 1 minus the completeness error. But the point is that whenever you have a valid instance witness pair, if you give me the correct proximity proof, I will accept with, say, probability 1. Okay? Then we have the proximity soundness condition that says, give me any pair, instance and witness. Maybe the instance is in the language, maybe it's not. Okay? Right now I'm not saying anything. The point is that no matter what, if the witness is far from any valid witnesses, what does far mean? Well, it's proximity parameter delta. So that's what it means. Then, regardless of which proximity proof should be tilde here, regardless of which proximity proof you consider, the probability you accept is small, okay? So the intent is you want to be convinced that the candidate witness is close to a valid witness. In the good case, if it really is a witness, then you accept. If it is far, you reject, okay? So, and what if there are no witnesses? Well, we're going to use the convention that the distance from a string to the empty set is maximal, is 1, okay? So that if X is not in the language, then you really are going to accept a small probability. But if X is in the language, there may be witnesses, but the particular candidate witness that you have access to, maybe it's far, and then you're going to reject anyways, okay? And again, notice that the verifier has 2 oracles. One is the witness about which we're talking about. The other one is chosen by the adversary. So this is kind of the picture you should have in mind. There are these 2 separate oracles. This is kind of, we know what it is. It's the thing we talk about. And this is chosen by the prover, okay? And the query complexity, now we're going to have to count queries to both the witness and the proximity proof, okay? So it's going to be the sum of both. So, and I guess I already said it, but even if X is in the language, the PCP verifier will still reject with a probability if W is far from from any valid witness, from all valid witnesses. So PCPs are really about proximity to valid witnesses, not just about membership in the language, okay? And hopefully, already syntactically here, you see how this is going to be helpful to us later, because in proof of composition, we want to talk about a particular local view. This syntactic feature means that we will be able to kind of sort of pass on this local view about which we're going to talk about to the inner verifier, okay? All right, other questions about the definition of a PCP of proximity? The only thing to keep in mind about PCPs of proximity is that they're not literally PCPs. It's a related notion. We'll see some other time that they do imply PCPs, but syntactically they're not. And they're about relations, not languages, okay? Okay, so if everybody's clear about what is a robust PCP and a PCP proximity, now we can prove composition. So now we can somehow refine our ingredients. We're still going to have an outer and inner, but now we're going to have a non-adaptive PCP for the target language with a certain robustness. Let's call it sigma out. And then we're going to have a PCP of proximity for specifically the relation given by the accepting local views of the outer verifier with some proximity parameter delta in, okay? So now the new PCP that we construct for, this should be L, for the language L, okay, is defined as follows. So we are just going to run the inner PCP of proximity on the correct local view with access to the chosen PCP of proximity. That's just the picture. Let's just see the pseudocode. Okay, what will the prover do? Well, the prover will say, okay, like before, like in the high-level plan, it's going to output the outer PCP as instructed by the honest prover of the outer proof system. Then, for each possible choice of randomness of the outer verifier, it is going to compute an inner PCP of proximity tailored to that one, and then it is taking into account specifically the correct local view. Okay, so here I should really say PCP of proximity. So this is a proof that is about, yes, this instance, about, yes, this choice of randomness, but it is about also this inner witness, because this proof of proximity will be about this witness. And then it outputs this whole thing. The verifier, like before, it is going to sample the randomness, the choice of randomness for the outer PCP verifier. And then it's going to run the inner PCP of proximity, where the inner instance is like this one, like before, but now we additionally have this inner witness that is specifically about the correct local view that we want to test proximity. Okay? And the analysis that this works actually is very straightforward. Kind of the definitions work in tandem extremely elegantly. The proof is like 3 lines. First line, if X is not an L, accept with probability epsilon out over the choice of the outer randomness, the local view, this one, is going to be sigma out far from an accepting view. Why? Because of the robustness of the outer PCP. Okay? I'm just stating the definition of robustness. Okay? Then, if that happens to be the case, and also we have this one condition that the robustness parameter for the outer PCP is at least the proximity parameter for the inner PCP proximity. If that is the case, that means that we have a witness that is far, and it means that the inner PCP will accept with probability at most epsilon in, which is its own soundness error, over the choice of its own randomness. So by union bound, we have an overall soundness error that is the sum of the 2 soundness errors. So the logic is like, it's directly from the definitions. In fact, those definitions were designed to make proof composition work. Okay? And the one thing you need to remember is that the robustness parameter for the outer proof system needs to be larger than the proximity parameter for the inner proof system, because the inner proof system wants things to be at least that far in order for its soundness condition to kick in. Okay? this is the proof that the construction is sound. And the high-level plan differs in the actual plan just basically in these minor changes, syntactic changes, but it really is that you're running the inner proof system on the outer verifier. Okay? Okay, so other questions about the soundness or syntactically what's going on here? Just to make sure, like the speed, the savings in query complexity is that this local view has a size number of queries of the outer proof system, but we're not going to be reading them all because we have at hand a PCP of proximity that will only sample a few of these locations of this large witness whose proximity to satisfying it wants to check. Okay? Okay. So we can state a proof composition theorem. This is just to kind of wrap up the construction into a usable statement. These are the same sort of ingredients as before, and with these ingredients, the theorem states that as long as we have this minimal condition, we're going to get soundness error that is the sum of the 2 errors. We just checked that. The randomness complexity is going to be the sum of the 2 because the new composed verifier will have to sample randomness for the outer verifier to determine the local view, and also the randomness for the inner verifier to actually run it. Okay, so that's like a pretty simple relation. Your randomness complexity just adds up. The proof length is, well, you're sending me the outer PCP and a bunch of inner PCPs of proximity. How many of them? Well, 2 to the number of randomness for the outer PCP. And something similar happens to the prover time, right, for the honest prover. And the query complexity is we're just paying for the query complexity for the inner proof system. And in fact, also, we get a speed up on the verifier time as well, because we're not actually running the outer verifier, we're just running a verifier that checks it. Okay? So, this proof composition theorem, basically as I've explained it, can also be used for saving on running time. There are 2 moreovers that I want to explain, both of which we'll be using eventually. in the eventual proof of the PCP theorem, we'll have to use proof composition twice in a row, okay? This is unlike, I guess, in code concatenation, where you really use concatenation only once to get a good code. To get a PCP theorem, we're going to use proof composition twice. Now, because we're going to be using it twice, we want to make sure that when we compose, we don't lose properties like robustness or proximity of the other proof system that we weren't using, right? So if, for example, after I compose once, I need the whole thing to be still a proof of proximity, I want to make sure that if I started with a proof of proximity rather than a PCP, I don't lose it by composing, okay? Because we'll have to compose again later. Sorry, I meant robustness, right? So let me say it precisely. So the outer, which for now, all we cared about for the outer was to be robust. But suppose the outer is in fact a PCP of proximity for a relation rather than a language, and has some proximity parameter delta out, then the composed proof system is a PCP of proximity for the same relation with the same proximity parameter. So if the outer, in addition to being robust, is a proof of proximity, then we don't mess it up through proof composition. Why? Well, in a construction analysis, just consider, kind of everything, like the argument about robustness, make it about not just pi out, like a local view on pi out, but a local view on the concatenation of the witness, whose proximity we're proving in the outer proof system. And for the soundness case, we're just going to consider a W that is delta out far, okay, from the set of valid witnesses. And so you can just do the same analysis, okay? And symmetrically, if the inner PCP is not just a PCP proximity, but in fact is a robust PCP proximity, then the composition will continue to be robust, okay? And again, this is like pretty simple, except with probability for the other proof system, we know that the local view is sigma out far from an accepting local view. If so, because of the PCP proximity, because of this condition, the local view, now this is like a local view of the local view, right? So, because now we're reasoning about the robustness of the inner PCP, right? So rather than saying that the local view, rather than saying that the inner PCP accepts with probability at most epsilon in, we want to talk about the local view of the local view is at most sigma in close to accepting with probability at most epsilon in, okay? So that, later we may again be able to apply proof of composition, okay? So, yeah, this is just a kind of cleanup, and we'll be using these properties when we use proof of composition multiple times. Are there any questions about the statement of the theorem or these perseveration properties? Right, you should ask questions. Today is a pretty easy lecture. It's not that technical. We have a few more things to say, but the main point is to just understand proof of composition. Proof of composition is actually, historically, it first came up in the proof of PCP theorem, early 90s. It's a very complicated proof. But about 10 years later, people formulated these notions of proximity and robustness. And it made sort of articulating this proof composition to be basically extremely, clear and simple. Once you have the right components, it's very simple to get out of the PCP theorem. And we'll see that we have to first build the components. Questions about this slide? Okay, so that's all I wanted to say about proof of composition for PCPs. We could ask, what about for IOPs? Okay. Like for example, we constructed linear size IOPs with logarithmic query complexity, right? How do we go to constant, right? For example, okay? And there are constructions, as I said at the beginning of the lecture, where you can get linear proof length and constant query complexity. I'm not aware of direct constructions, none that achieve that, but you build ingredients and then you invoke proof of composition for IOPs, analogously to what you do for PCPs. Okay? So here we can similarly define robust IOPs and IOPs of proximity. And I have two definitions that I'll show, and I have highlighted the small things that change. Okay, well, first, if you want to define an IOP, the thing that changes is you replace PCP with IOP. That seems like an easy change. Okay, robustness parameter. The completeness condition is the same as usual, with the usual mistake. That, if X is an L, then everything happens like normal IOP rather than normal PCP. And the robustness condition is, well, it's the same condition as before, except that the only thing that you change is that you define the proof about which you're taking local views to be the concatenation of all the oracles that were exchanged during interactive phase. Okay? Now, what is the interactive phase? Well, just like for a PCP, when we define robustness, we had to talk about non-adaptive IOPs. And for non-adaptive IOPs, all the queries can just be at the end. And so that means that while the verifier is chatting with the prover, they're just exchanging messages and there is oracles being kind of piled up during the interaction. When you're done with interaction, you just kind of concatenate them all, right? And that is the thing about which you're taking local views. Okay? So robust IOP means that with probability at most epsilon s, after interaction, when you look at the local view, it is closer than sigma when you restrict it to local view. Okay, so there's really basically no change. Before we were just kind of letting pi tilde be the PCP. These are just the PCPs accumulated during an interaction. Okay, and the probability is taken over kind of the whole randomness of the whole verifier. Okay, so it's a very kind of compact and sort of, I think, clear generalization of what is a robust IOP, a robust PCP. This isn't a robust IOP. Okay, what is an IOP of proximity? Well, we have, we're talking about an IOPP rather than a PCPP. We still have a proximity parameter. Well, we have, we're interacting in the good case rather than just the prover sending one oracle. And proximity soundness, just like before, I make explicit the fact that I have a particular witness to talk about, that W, and all of the other oracles are whatever I'm exchanging, okay, like always, during the interaction, okay? We have the same convention, and that's it. So, I mean, we're about to talk about interactive proof of composition, but other questions about these definitions. Like, once you understand robustness and proximity for PCPs, kind of formulating them for IOPs, it is it's a good exercise to even try to do it by yourself, kind of, without looking at the slides. It's very straightforward. Okay, you have to remember that for robustness, you can only look at things that are non-adaptive. Okay. And for proximity, you always have to put the witness to be explicit oracle to the verifier, okay? And talk about relations, okay? Now, for IOPs, we can similarly define interactive proof of composition, which in fact, it will turn out to be more efficient than its non-interactive counterpart, again, thanks to interaction. This is like a theme that we've seen many times, that by using interaction, we're going to be able to make things cheaper, okay? By kind of giving an opportunity to the verifier to send the randomness rather than the prover kind of being prepared for every choice of randomness. Any questions about this slide? We're about to kind of talk about proof of composition for IOPs. Okay. So we again have an outer and we have an inner. We have a non-adaptive IOP for language L with robustness sigma out. We also have an IOP of proximity, okay, rather than a PCP of proximity, for the relation of accepting views of the outer verifier with a certain proximity parameter. For composition, the new IOP verifier, like the main change we're going to do is that the verifier is going to tell the IOP prover which randomness it chose, so that we don't have to like go over all choices of randomness. So pictorially it looks like this. The verifier samples the randomness for the outer verifier. It still has to go through the interactive part of the outer verifier, so it just does that, okay? It's a non-adaptive IOP, so nothing really is happening. The verifier is just sending messages to the prover so that the prover knows, what PCP to send next. Anyway, they go on like this for some number of rounds, but no queries have been asked. Again, it's a non-adaptive IOP. Also, at the end of this interaction, no queries will be asked because there's too many queries to ask. Remember, we wanted to reduce the query complexity of the outer IOP, okay? So at this point, the verifier feels safe to send, you know what, like, I chose this randomness, let me tell it to you, okay? There is no need to run an inner IOP for every choice of randomness. We're just going to tell the prover, hey, I chose this randomness. What is the prover going to do? He has already done with the interactive phase. There's nothing he can affect anymore about the outer interaction. He has no more moves to make about that protocol. So we're going to tell him which randomness we chose, so that we only have to run one instantiation of the inner IOP of proximity, okay? Which is going to have a particular witness, which is whatever is defined as a local view from the transcript so far, given this choice of randomness. Again, I'll say it for the nth time, the prover is not running the inner proof system for every choice of randomness. It just asks the verifier to tell it what randomness it wants. This doesn't break soundness because the interaction, all the moves for the outer proof system have already been played. There's nothing else for it to affect anymore. Okay, so it's safe to tell this randomness. So the analysis is the same. The difference is the way the theorem looks like, that we have some savings. Okay, so the error is going to look the same because by the same analysis, the round complexity adds up. Okay, maybe there's a +1 here, but I think you can like pipeline it either above or below, and then you still get the same round complexity. The randomness complexity adds up. Okay, but crucially now the proof length, there is no, you have this 1 times rather than 2 to the r out times. Okay, and that's also true for the outer, for the prover time. Okay, so we're just adding up the proof lengths rather than having this blow up. Okay, intuitively, by the way, this is one of the key speed ups in a kind of very general sense of IOPs. Okay, you can think of many of the things we've done in the past, interactive reductions, as some sort of proof composition. Not exactly precisely, but intuitively that's what's going on. And here, yet again, you see this kind of speed up. The query complexity, we're going to be paying just for the one internally. And the verifier time, well, yeah, we do have to spend time to run the interactive part of the outer proof system. And then we're going to run the inner proof system. But usually, and I'm just going to put a cross over it, because usually we have public coin IOPs anyhow, and just representing what is the choice of randomness for the outer proof system, we already paid for the interactive part. And so this thing is going to be at least the size of the outer randomness. So it is just running the inner proof system, okay? And then we had a moreover in the 2 slides ago, and the same moreover holds, right? So if the outer IOP is a proof of proximity, then the composed proof IOP is also proof of proximity. If the inner IOP is a robust IOP of proximity, then the composed thing is robust, okay? Questions about interactive proof composition? Compared to other things we've seen in other lectures, I really want to say clearly, proof composition is easy. There are 2 simple definitions and they're made to dance together. And they dance together in a pretty simple construction, all right? Okay, so I kept today a little bit on the lighter side. The plan for the next 2 lectures is pretty simple. We want to achieve the PCP theorem. We have figured out that we need not just PCPs, but PCPs with these extra properties. But these extra properties, we just made them up. So we cannot just go back and take off-the-shelf PCPs that we had and use them here. We're going to have to modify them so that they are robust and of proximity. Okay, so we're going to have one lecture on constructing robust PCPs and one lecture on constructing PCP proximity. And in that second lecture, we'll be able to then come back here to this generic infrastructure and then kind of put it together and get the PCP theorem. Okay, so we'll be seeing things called robustification. It's a generic paradigm. And we'll be seeing how to basically generically construct proofs of proximity, almost. It's not quite completely, but for the most part. And both of those are like highly recurring patterns in sort of design analysis of probabilistic proofs. In particular, I would say like almost every recent advances in probabilistic proofs has been made through some type of proof of composition. And yeah, so let me stop the recording.